Okay, so let's try some of those concepts now. So find the probability if you were to choose one card from a deck of 52 cards, standard deck. Find the probability of choosing a black or a queen. So there are cards that are blacks and queens. So we have to keep in mind that there's an overlap here. So the probability of choosing a black is going to be 26 out of 52 because there are 26 black cards. So it's going to be the probability of choosing a black, 26 out of 52, which is one half. Half the cards are black. And then add that to the probability of choosing a queen, which, notice how there are 4 queens, so 4 out of 52. But notice how these cards here got counted twice. So we would have to find, since we counted them twice, we want to subtract the probability of choosing a black and a queen. Alright, this means two sets are the overlap of both sets, means and. This is the union of two sets, so it's like or. So black intersection queen is the probability of choosing a black and a queen. Whereas like black or a queen is what we're trying to find right now, like the probability of doing one of these things that I highlighted in purple or orange. So that probability is going to be 2 out of 52 because there's 2 black queens. So now we're going to add all that up, and we get the probability is 28 out of 52, and you should always simplify that, and that simplifies down to 7 out of 13. So if you pick a deck, if you pick any card from a deck of cards, there's a 7 out of 13 chance that it is a black card or a queen. Okay, now in this example, find the probability of choosing a heart or a black. Alright, they are not. They are mutually exclusive. If we look at all the hearts, there they are. There's 13 hearts. So the probability of choosing a heart is 13 out of 52. If I highlight all the black cards, notice how there's no overlap. There's no black hearts. So there's a 26 out of 52 chance of doing that. So we don't have to subtract any overlap. Because they're mutually exclusive, we could just add them together. Add them up, simplify it, and you get a probability of 3/4. Okay, another important topic in probability is independence. So some events are dependent on each other and some are independent. So 2 events are independent if, what happened here? Sorry. Are independent if one has no effect on the other. Okay, my pen is not working. Here we go. So if you roll a 4 on a die, it's independent on flipping tails on a coin because there's no effect on, like, what you roll on a die has no effect on what you flip on tails. And actually, every time you roll a die, it's independent of the next roll. If you roll a die and it's a 4, and then you roll it again and it's a 4, and then you roll it again and it's a 4, on that 4th roll, there's still a 1 out of 6 chance you roll a 4. And it kind of, if you ever go to a casino, and you probably haven't because you're not 21, but if you ever play roulette, alright, roulette is this wheel and there's 30 numbers on it, and half of them are black and half of them are red. And a lot of people will bet that the next row will be red or black. And next to the table, they'll have like a chart, and it'll show like, oh, okay, the last 4 rolls were red, and then a black, and then a red, and then 2 blacks, and then a red. And if these are the last 4 rolls here, someone might say, oh, I'm going to bet black because there's a really good chance black comes out because there were just 4 straight reds. And that is absolutely wrong. Alright, every roulette spin is independent of the next one. You can roll black, you can spin red 100 times. There's still going to be a 50% chance there's a red on the next roll. That's what independence means. Now, not all events are independent of each other. When you play blackjack, alright, the reason why you're able to count cards is because one event is not necessarily independent from the next one. When you play blackjack, they take these cards from these big decks of cards. So if you notice that they take out like a lot of aces, let's say, well, they haven't replaced the aces, so now there's a smaller chance that the next card will be an ace. So that would be an example of dependence. Alright, so a common place of dependence is when you choose a card from a deck and you don't replace it. Alright, let's say I just had one deck of cards and I flipped over an ace. And I flipped over an ace again. I didn't replace them. Now, instead of there being a 4 out of 52 chance that the next card's an ace, there's going to be a 2 out of 50 chance it's going to be an ace because there's 2 less aces. So the chances go down. That would be dependent. Alright? So sometimes I'll tell you when things are independent of each other. Sometimes you have to think.